Hi, class. So we finished up talking about modern physics with quarks and leptons and so forth, and we're going to now talk about some more macroscopic concepts that we see that apply to large objects. Okay? And we're going to talk about work and energy today. We'll maybe introduce conservation of energy. Um, and so let's introduce work and energy by looking at a roller coaster video. Uh, And so let's go here. All right. And what you see here is a roller coaster. And we are we're moving up a roller coaster. So we started at the very bottom of the roller coaster and we're getting pulled up a roller coaster. You can see here there's a little black chain here. The roller coaster is attached to this black chain and it's getting pulled up higher and higher and higher. And we say work is being done because a force is being applied to an object, causing that object to move through a distance. That's what work is. Work is force times distance. All right. And so work is being done to raise this roller coaster up to a height. All right. So now here we are up at the top of the roller coaster and we have lots and lots of height. All righty. Oops. Sorry. Okay. So we saw the roller coaster get lifted to the top uh, of its height. And that's what work is. Okay, so work is, as I said, whenever we apply a force to an object through a distance. So, for example, if a man lifts a box, he's applying a force to that box and moving it through a distance. We say work is being done. All right. Whereas here we have a picture of a man, and we know that this weightlifter had to do work to lift the weight up above his head. But if we said now that he's got it above his head, and the weightlifter is applying a large force to hold this barbell over his head, how much work is he doing while he's holding it, while he's just holding it steady above his head like that? The answer would be he's doing no work while he's holding it because he's no longer moving it through a distance. Right? So work is force times distance. Both things need to apply in order for work to be done. All right, so let's just do an example. If a man lifts a 50 Newton box up a height of half a meter, how much work did he do? And the answer is the work is the force times distance. So it would be 50 Newtons worth of force causing an object to move 0.5 meters would be 25 joules of work. So this man applied a 50 Newton force to lift this box up half a meter. He applied the force the whole time he was moving it. So we would say he did 25 joules of work. The unit of work is joules, right? So work and energy both have the same units of joules. Now let's look at a second example. Here, a weightlifter holds a 600 Newton weight, but he doesn't move it. How much work does he do while he is holding it? Well, the force would be 600 Newtons, but the distance would be 0 because he's just holding it. He's not actually getting it to move. So we would say he's doing 0 joules of work. Okay, so in order for work to be done, the object has to move. All right, now we want to talk about energy. We're going to talk about two types of energy: gravitational potential energy, which is energy due to height, and kinetic energy, which is energy due to speed. All right, so let's go back to our video because now we're at the top of the roller coaster. So work has been done. We applied a force to the roller coaster and moved it through a distance. We moved it up that big hill. Now it's at a much higher distance. And because it's up here, we say it's got gravitational potential energy. Okay, it's way up here at the top. You can see trees out here in the back. There's a parking lot over here. But this roller coaster is way up in the air. It's not moving really very fast at all yet, but it has got a lot of height. So we say it's got a lot of gravitational potential energy. It's got a lot of energy due to its height. All right, that's gravitational potential energy. And now you can see that chain that we spoke about before is no longer there. So all that's happening is that the roller coaster is now going to be falling down just due to gravity. So now it's just going to be coasting along the track. All right. So now as it's falling down, it is going to pick up some speed. All right, and right here it goes down a big hill and zoom, it's going very fast. Okay, so right here it's at the bottom and it's moving very fast because all that energy due to its height, all that gravitational potential energy, now you can see we're down towards the ground again. We're not no longer way up in the air, but we're going fast now. So that we say the energy due to its height, its gravitational potential energy, has been now converted into energy of speed or kinetic energy. All right, and then it goes back up. It does a loop-de-loop. Now, every time it goes back up in height, it's going to slow down. So as it goes up in height, it slows down a little bit, and then as it comes down back towards the ground, it speeds up again. So when it goes up and gains back some of its gravitational potential energy, it slows down. It gives up some of its kinetic energy. So there's a continuous trade-off between height up here. When it's high up, it's got lots of potential energy, and when it's down, it's got lots of speed energy. Okay, so the way this roller coaster works is there's the energy keeps kind of going back and forth between energy of speed. When it's low down, all the gravitational potential energy will have been converted to kinetic energy of speed, and then when it goes back up again, it gives back some of the speed, but it gains back height. So there's a conversion between speed energy when it's low and gravitational potential energy when it is high. All right. I'll give you that video to look at, and you can take a look at that. All righty. All right, so let's go over these two types of energy in a little bit more detail. So we said there were two kinds of energy we saw in that roller coaster. We said gravitational potential energy, which is energy due to height. And we actually have a formula for that, which is mass times gravity times height. So the mass of the roller coaster, or the mass of whatever object you have, times gravity, which is 9.8 meters per second squared, times height. So the more height you have, because in most situations, mass is going to stay the same, like the mass of the roller coaster is going to stay the same. Gravity is a constant, 9.8. What's going to change is height. So as you gain height, you gain gravitational potential energy. As you lose height, you lose gravitational potential energy. Okay, so gravitational potential energy is mass times gravity times height. Kinetic energy is energy due to speed, and its formula is 1/2 mass times velocity squared. So 1/2 times the mass of the object times the speed of the object squared, or the velocity of the object squared. And so here we have a couple of examples. This is called a pile driver, and what it is a big stone on a rope or a wire, and then there's a motor back here that lifts the stone. So the stone gets pulled up, 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 up. So it gains a lot of gravitational potential energy. We say the motor is doing work because it's applying a force to this rock through a distance. And so it gets up, 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 up. And then the stone, they release it, and the gravitational potential energy converts to kinetic energy, and it accelerates, 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 and then slams into a pole, and that pole drives into the ground. Okay, so we say that there's a conversion between gravitational potential energy and kinetic energy, and then the kinetic energy does work on the object, applying a force on the object through a distance, driving it into the ground. And I'll send you a video on a pile driver as well. And this is an example of kinetic energy. Here we have a tank crashing through a wall. So the tank is applying a force to the wall and causing the wall to move through a distance. It's crashing through the wall, and all these bricks are have a force applied to them, and is moving those bricks through a distance. And we say that this tank has a lot of kinetic energy because, let's look at our formula for kinetic energy. 1/2, that's just a number. Mass, well, the mass of the tank is going to be very large. There's lots of metal here. And velocity to the second power, so velocity times itself. So the tank might have a lot of velocity. It might be moving at 20 meters per second. And and that number would be squared. So kinetic energy, but again, just like with gravitational potential energy, kinetic energy, the mass of an object is usually going to stay the same. What's going to change is the velocity of the object. So as we make the tank, as we hit the gas and make our tank go faster and faster and faster, we're increasing the kinetic energy of our tank. So kinetic energy is related to speed, whereas gravitational potential energy is related to height. Okay? And then the last thing we really want to talk about today is that something that we spoke about in the roller coaster videos, the work energy theorem. And that's when you do work on a system, you change the system's energy. So for example, when we lifted the roller coaster up, we changed the gravitational potential energy of the roller coaster. Okay, so when we pulled that roller coaster up, we changed its gravitational potential energy. So the work changed the energy of the roller coaster. We increased the gravitational potential energy of the roller coaster. Okay, so for example, if work is done to increase an object's height, there's an increase in the gravitational potential energy. Here's another example of work converting to energy. So we said work is force through a distance. Well, this baseball right now is not moving, but when Mariano Rivera applies a force and pushes this baseball, he's going to accelerate it, get it up to maybe 100 miles an hour. And that baseball then has a lot of kinetic energy due to its velocity. So by doing work to the baseball, applying a force on it through a distance, he is changing the energy of the baseball. Right now, that baseball has zero kinetic energy. It's standing still. But in a moment, that baseball will have lots of kinetic energy, and it will have that kinetic energy because he did work to it. So if the work increases the motion, there's an increase in kinetic energy. You could also do work to compress a spring, and not all work, um, not all work results in an increase in gravitational potential energy or kinetic energy. Sometimes, for example, if we just push a book across a desk, um, the uh, the we're not making the book any higher, so we're not giving it gravitational potential energy. And if we push a book along at a constant speed, we're not making it any faster, so we're not increasing its kinetic energy. So we would say, well, where's that work going to? What kind of energy are we giving that book in this case? Well, in this case, we would say that the book, what's actually happening is the surface of the book is getting a tiny bit warmer, and in this case, the work is being converted into heat energy, or what we call internal energy. Okay, so in many situations, the work that's being done will either convert to an increase of gravitational potential energy, an increase of kinetic energy, or an increase of heat energy, or what we call internal energy. Alrighty, so I think that's enough for today. Next time we will talk about conservation of energy, so how energy can be converted, like we saw in the roller coaster. We saw that conversion from gravitational potential energy at the top to kinetic energy at the bottom. We'll talk about that in more detail next time as we get into greater detail on the law of conservation of energy. Alrighty, so hopefully this was a good introduction to work and energy. And so please answer the questions in the quiz form and then submit that. Alrighty, thank you.